In this section, we're going to take a look at a rather important concept within fluid mechanics, and that is what we refer to as being the no-slip condition. And if you recall from an earlier segment, we've been discussing viscosity and the relationship between shear stress and shear rate in a fluid. And what we said was that for what we call a Newtonian fluid, we have this relationship so we have that relationship between shear stress and shear rate. And now for the no-slip condition, so what the no-slip condition does is it basically specifies what happens along the boundaries. So let's say our fluid is next to a wall. The no-slip condition gives us information about what is happening exactly on that wall. And for fluid mechanics, what we say is there is no slip along the wall. And what that means that if the wall is moving, the fluid will be moving with the wall. And if the wall is stationary, the fluid right on the wall will be zero. So let's take a look schematically what we're talking about. So imagine we have an upper wall and a lower wall. And for this particular case, we'll say that the lower wall is fixed. And if it's fixed, it's not moving. Consequently, the velocity is equal to zero. And let's imagine that the upper wall is moving. And between these two plates, we have a fluid. And our velocity profile may look something like this. And then that u would be a function of position, or y. With the no-slip condition, what we know is that the velocity at y equals 0. So on the lower wall, if it is fixed, it will be equal to 0. And on the upper wall, the velocity there will be equal to the wall velocity itself. So what no-slip says is that the fluid will be moving at the same velocity as the location of the wall. So if the wall is fixed, it's not moving. If it's moving, it is at the wall velocity. Now, it turns out that there are some applications where you can actually see this. And this is typically within the boundary layer around an object. Here we're looking at two plates. That could be, for example, a bearing, where you have two planes moving with respect to one another, or one plane not moving. Another place where we can see this, and we're going to take a look at a video example of this, is in aerospace applications. So let's take a look at a short video clip here. So in Canada in the winter, quite often we get a lot of snow buildup on the runways and on the aircraft, and we have to apply a de-icing agent to the aircraft to prevent formation of ice or snow buildup, which could have an impact upon the control surfaces or even the shape of an airfoil of a wing. And so there you can see anti-ice agent being placed onto a wing, and here's a wing that has been covered with this anti-icing agent. On takeoff, this anti-icing agent is a liquid, and so there you can see the liquid coming off the wing as the aircraft is accelerating. And then once you climb and get up to altitude or elevation for the flight, what's interesting, you can still see the liquid moving. And so here's an image at 217 meters per second, so that's about Mach 0.72. And you can still see the anti-icing agent moving on the wing very, very slowly. But what that is showing is that even though the aircraft is moving at 217 meters per second, the fluid right along the surface is not moving. And the liquid is just moving very, very slowly because it's thicker than the profile, than the surface. And so it gets shear and it moves along. But that gives you an example showing you evidence that there really is the no-slip condition. Sometimes it's something that a bit of a theoretical construct and it's hard to see, but with that video clip you get an idea as to the fact that really the fluid right along the wall, even though the plane was moving at 217 117 meters per second, the fluid along the wing section right on the top of the airfoil is not moving. So that's no slip. Another one that we have is if you have non-isothermal flows, and we refer to this as being the no temperature jump condition. So this would be an application perhaps in heat transfer, and what we'll do, we'll draw out the two planes again just like we did before. We have our upper wall, our lower wall. And again, let's assume that the upper wall is moving. We have our velocity profile as before. Now, with temperature, we will have a temperature at the lower wall, so that might be T1. And if there's heat transfer taking place, we could have a different temperature at the upper wall, so we'll call that T2. And between the two, there will be some profile. It does not necessarily need to be a linear profile. It depends upon what the fluid is doing and if it's turbulent or laminar or anything like that. But what we say is that T at y equals 0, so at the lower wall is going to be equal to the temperature of the lower wall, and T at y equals y1 is going to be equal to the temperature of the upper wall. So that's the no temperature jump condition. So the fluid right along the wall will be the same as the temperature of the wall itself. And through heat transfer, we'll have conduction going through, so there would be heat flowing. It would come in through conduction, and then it would leave through convection or radiation, depending upon the fluid and the temperature of the wall. So that's the no slip and the no temperature jump condition. They are boundary conditions that we will apply when we're studying things. Quite often, the no slip is the one that we will use quite often if we're trying to solve for a velocity profile. Two very important concepts within fluid mechanics: no slip and no temperature jump.